All right, time to do like 4 examples of L'Hopital's rule. And this is not the end. We're going to do more after this. But let's just start with some basic ones. Let's look at the limit as x approaches 0 of e to the x minus 1 over x. This is the limit that I showed you on the first in the first page to sort of introduce the indeterminate form. Now that we know L'Hopital's rule, we can tackle this. So this is approaching 0 over 0. It is in the indeterminate form, so we can apply L'Hopital's rule. And what I'm going to do is I'm going to write equals, and I'm going to put a little h above the equal sign when I apply a L'Hopital's rule. And I encourage you to do the same, because it makes it a little easier for me to grade, because I can see when you're applying the rule. So this is going to be equal to the limit as x approaches 0 of the derivative of the numerator. So if we just differentiate e to the x minus 1, we get e to the x minus 0, divided by the derivative of the denominator, which is 1. Okay, so that equality there is justified by L'Hopital's rule, which is what the h represents. Now this is no longer indeterminate, because as x approaches 0, e to the x is going to be approaching 1, and 1 is going to approach 1, so that's 1 over 1, which is 1. So L'Hopital's rule has made this limit exceedingly easy to solve, and it just equals 1. So that was nice. Let's look at the other one. The other one we were looking at was the limit as x approaches infinity of this same function, which, as we saw before, the numerator is approaching infinity and the denominator is approaching infinity. So this will equal, by L'Hopital's rule, the limit as x approaches infinity of the same derivative ratio, e to the x over 1, which e to the x is approaching infinity as x approaches infinity, right? That's off on the right side of e to the x where it diverges, and the denominator is approaching 1, so that's going to be getting close to infinity. All right, let's do a couple more. Limit as x approaches 0 of sine of x over x. Does that sound familiar? Back in chapter 2, we did this beautiful and long and complicated proof that involved a bunch of geometry and trigonometry, and then it used the squeeze theorem, and we were able to prove that this limit is equal to 1. This limit equals 1. Now that we've learned L'Hopital's rule, turns out we don't need all that huge long proof we did with the squeeze theorem and all the geometry and stuff. None of that is necessary. Because if we have L'Hopital's rule, and we see that this is in an indeterminate form, sine of 0 is equal to 0, right? And x would be 0. So this is approaching 0 over 0. We can apply L'Hopital's rule and do derivatives. The derivative of sine of x would be cosine of x, and the derivative of x will be 1. So there's the derivative, here's the ratio f over g, and here's the ratio f prime over g prime. But now what's this limit? This is not indeterminate, because as x approaches 0, cosine of x will approach cosine of 0, and then 1 is, of course, approaching 1. And this, cosine of 0 equals 1. So there we go. So that's that limit. Cosine of 0 is 1. So that makes it super, super easy to prove that limit equals 1, which makes you wonder why we did all that stuff before. Well, it's because we hadn't learned about derivatives yet, of course. One more example. Let's look at the limit as x approaches infinity of the natural log of x divided by x. Okay, the natural log of x divided by x. As x approaches infinity, the natural log of x also approaches infinity. That, draw the log graph, right, like this, right? I know this is leveling off over here. It's kind of getting shallower. It's getting more level, but it never actually approaches some finite value. There's no horizontal asymptote here. This does indeed go up forever towards infinity. Okay, so that's the limit of natural log on the right. And then, of course, x is approaching infinity. So this is an infinity divided infinity, and so that's indeterminate. And then we can apply L'Hopital's rule and get the limit as x approaches infinity of the derivative of natural log of x, which is 1 over x, divided by 1 again. And this is 0, right? Because 1 over x is going to be approaching 0 as x approaches infinity. So L'Hopital's rule is amazing because it takes limits that are seemingly impenetrable, right? Limits that you have really no idea how to tackle natural log of x over x, as x approaches infinity, it's very difficult to approach that, but L'Hopital's rule can convert it to something super simple and easy, potentially, okay? It's not guaranteed it'll be easier, but it is often super useful. Now, I want to issue a word of caution about L'Hopital's rule. I mentioned that it only applies to 0 over 0 or infinity over infinity cases. Lots of exclamation points. If you are in any situation that is not 0 over 0 or infinity over infinity, then it does not apply, and in fact will give you the wrong answer. Let's look at an example. If you look at the limit as x approaches 2 of x squared minus 1 over x plus 2, this is in fact a limit that can be evaluated with direct substitution. This is 2 squared minus 1 over 2 plus 2, which is 4 minus 1 over 4, or 3/4. That is the correct answer. Okay, it's just, 2 is in the domain of this function, so you just stick it in there, and you get 3/4. If, on the other hand, you were to accidentally attempt to apply L'Hopital's rule to this, you would take the derivative of the numerator and get 2x, and the derivative of the denominator, which would be 1, and then the limit of that ratio as x approaches 2 is just equal to 4, which is not the same. And the reason is because you shouldn't use L'Hopital's rule on this. In fact, the proof of L'Hopital's rule, which I know I haven't shown you, but you can read it in the textbook if you'd like. I think it's in one of the appendices. The proof of L'Hopital's rule really relies on the assumption that you are in either a 0 over 0 or infinity over infinity scenario, okay? So not having one of those cases means that L'Hopital's rule will not work, and if you attempt to do it, it'll give you something that is not correct. So that's my word of caution.